Welcome to a journey into the enigmatic and often misunderstood realm of quantum physics. Today we're exploring one of the most intriguing aspects of this field, the PilotWave Theory, also known as the Broglie-Bohm theory. This alternative interpretation of quantum mechanics challenges some of the most fundamental ideas about the behavior of particles at the quantum level. Quantum mechanics, a cornerstone of modern physics, has provided us with an incredibly successful yet perplexing picture of the subatomic world. It describes a reality where particles exist in a haze of probability until they are observed, where the act of measurement affects the measured, and where particles can be entangled over vast distances. However, this standard quantum model, for all its predictive power, leaves many questions unanswered, especially regarding the true nature of reality. In the early 20th century, amidst the quantum revolution, French physicist Louis de Broglie proposed a bold new idea. He suggested that particles at the quantum level might actually behave like tiny waves spreading out in space. This wave-like behavior could explain the strange and probabilistic outcomes seen in experiments. However, de Broglie's initial ideas were overshadowed by the more dominant Copenhagen interpretation, which focused on the probabilistic nature of particles without assigning them definitive paths. The concept of pilot waves saw a resurgence in the 1950s thanks to the work of physicist David Bohm. Bohm, dissatisfied with the prevailing interpretations of quantum mechanics, revisited de Broglie's ideas and expanded upon them. He proposed that particles are indeed particles, but they are guided by a pilot wave that determines their trajectory. In Bohm's view, this pilot wave is a real physical wave that exists in addition to the particles, guiding their motion in a deterministic way. Under the PilotWave theory, the bizarre and probabilistic nature of quantum phenomena can be explained in a more intuitive manner. Instead of particles existing in a state of probability until observed, they have definite positions and velocities at all times, guided by the pilot wave. This wave is influenced by the overall environment, which means the particle's path is determined not just by the wave, but also by the entire configuration of the universe. This reintroduces determinism into quantum physics, a stark contrast to the randomness inherent in the standard interpretation. One of the most famous demonstrations of quantum mechanics is the double-slit experiment, where particles exhibit both wave and particle characteristics. In the standard interpretation, the act of observing the particle seems to collapse its wave function, determining its position. However, in the PilotWave theory, the particles always go through one slit or the other, with their path influenced by the guiding wave, which passes through both slits and interferes with itself, guiding the particle to specific points on the screen. The implications of the PilotWave theory are profound. It suggests a universe that is deterministic and continuous, where the weirdness of quantum mechanics is a result of our limited perspective of this underlying pilot wave. It brings back a classical sense of order to the quantum world, but at the cost of introducing non-locality where distant particles can affect each other instantaneously through their shared wave. Despite its appeal, the PilotWave theory is not without controversy. One of the biggest challenges is that it introduces non-locality at a fundamental level, which seems to conflict with the theory of relativity. Additionally, because the theory is deterministic, it implies that the entire history and future of every particle in the universe are predetermined, raising philosophical questions about free will and the nature of reality. As we delve further into the PilotWave theory, we encounter both its elegance and its complexities. This theory, while not mainstream, continues to attract attention for its unique approach to quantum phenomena. Let's explore more about its implications, challenges, and the ongoing debates in the scientific community. The concept of non-locality in PilotWave theory suggests that information or influence can travel instantaneously between entangled particles, no matter the distance. This idea, while seemingly at odds with Einstein's theory of relativity, which states that nothing can travel faster than light, is actually supported by quantum experiments. The theory posits a deeply interconnected universe where distant events can be intrinsically linked in ways that our classical understanding of space and time cannot explain. In recent years, PilotWave theory has been formalized into what is now known as Bohmian mechanics. This modern interpretation provides a more mathematically rigorous framework that aligns with de Broglie and Bohm's original ideas. Bohmian mechanics not only offers explanations for standard quantum experiments, but also opens up new avenues of thought in quantum theory, including potential insights into the quantum to classical transition and the measurement problem in quantum mechanics. One of the challenges in assessing the pilot-wave theory is the lack of direct empirical evidence distinguishing it from the standard quantum model. Because both theories predict the same outcomes in standard quantum experiments, it's difficult to design an experiment that can conclusively favor one over the other. However, researchers continue to explore creative ways to test the unique aspects of the pilot-wave theory, particularly its implications for non-locality and determinism. The deterministic nature of the pilot-wave theory brings with it profound philosophical implications. If the universe operates on predetermined paths guided by a pilot wave, it challenges our notions of probability, uncertainty, and even free will. This deterministic universe is a shift away from the probabilistic nature of the Copenhagen interpretation and opens up philosophical debates about the nature of reality and our understanding of it. Despite its intriguing prospects, the pilot-wave theory remains on the fringes of mainstream physics, primarily due to its non-local characteristics and the philosophical questions it raises. However, its ability to provide a different perspective on quantum phenomena keeps it relevant in theoretical discussions. As our understanding of quantum mechanics continues to evolve, so too will the exploration of alternative theories like the pilot-wave theory. The future of the pilot-wave theory may lie in its integration with other areas of physics. Efforts to reconcile it with general relativity, quantum field theory, and even dark matter research are ongoing. These interdisciplinary approaches are crucial in advancing our understanding of the universe and may eventually lead to a more unified picture of physics. In conclusion, the pilot-wave theory represents a fascinating and unique perspective in the world of quantum mechanics. It challenges us to think differently about the quantum world, offering a deterministic and interconnected universe. As we continue our scientific journey, theories like the pilot-wave theory remind us that there are always new ways to understand the cosmos. The quest for knowledge is never-ending, and alternative theories play a crucial role in pushing the boundaries of our understanding and sparking the imagination.